When dealing with a motor control center (MCC) that qualifies as a service entrance with a 1600 amps bus design, understanding how to properly size the overcurrent protection device (OCPD) is crucial. The National Electrical Code (NEC) Section 230.90 provides the guidelines for this. You are allowed to size the OCPD in the main entrance based on the ampacity of the conductors. This means you can calculate the conductor ampacity by summing the full load amps FLA of all the motors plus 125% of the largest motor's FLA. This method provides adequate protection without necessarily invoking exception 1 in 230.90. Exception 1 provides an alternative approach. This exception is permitted, meaning you have the option to use it, but it is not a mandatory requirement. The code allows for flexibility in design, so long as the chosen method ensures adequate protection of the conductors and equipment. When deciding whether to use the standard ampacity calculation or to invoke exception 1, several factors should be considered. Firstly, consider the specific load characteristics of the motors being served by the MCC. If the motors operate under consistent and predictable load conditions, the standard ampacity calculation might be sufficient. However, if the motors experience frequent starts, stops, or variable loads, exception 1 might offer a more conservative and appropriate level of protection. Secondly, evaluate the coordination of the overcurrent protection devices within the entire electrical system. The OCPD at the service entrance should be coordinated with downstream OCPDs to ensure selective tripping. This means that only the OCPD closest to the fault should trip, minimizing disruption to the rest of the system. Exception 1 might provide an advantage in achieving better coordination in certain situations. Thirdly, consider future expansion or changes in the motor loads connected to the MCC. If there is a likelihood of adding more motors or increasing the size of existing motors in the future, it might be prudent to use exception 1 to provide additional capacity and avoid the need for future upgrades to the service entrance OCPD. When calculating the conductor ampacity, accurately determine the full load amps FLA of each motor. This information is typically found on the motor's nameplate. Use the correct values to ensure accurate calculations. Additionally, when applying the 125% factor to the largest motor's FLA, be sure to identify the motor with the highest FLA value correctly. This will ensure that the OCPD is sized appropriately to handle the inrush current during motor starting. It's essential to verify that the calculated ampacity of the conductors is sufficient to carry the load current, including the 125% factor for the largest motor. Consult the appropriate tables in the NEC, such as Table 310.16, to determine the allowable ampacity of different conductor sizes and insulation types. Ensure that the conductors selected have an ampacity equal to or greater than the calculated load current. When selecting the OCPD, choose a device with a rating that is equal to or less than the ampacity of the conductors. This ensures that the conductors are protected from overcurrent conditions. The OCPD should also have an interrupting rating sufficient to handle the available fault current at the service entrance. This prevents the OCPD from failing during a fault condition. Ensure that the OCPD is properly labeled and marked with its ampere rating and interrupting rating. This provides clear identification for maintenance and troubleshooting purposes. If you choose to use exception 1 in 230.90, carefully follow the requirements outlined in the exception. This might involve calculating the maximum allowable OCPD rating based on the sum of the motor full load currents plus a specific percentage of the largest motor's full load current. The specific percentage will be defined in the exception. Be sure to document all calculations and assumptions made during the OCPD sizing process. This documentation will be valuable for future reference and for demonstrating compliance with the NEC. It is always recommended to consult with a qualified electrical engineer or inspector to ensure that the OCPD sizing complies with all applicable codes and standards. They can provide guidance based on the specific characteristics of your installation and help you make informed decisions. Remember that the electrical codes and standards are subject to change, so it's essential to stay up to date with the latest revisions. Regularly review the NEC and other relevant publications to ensure that your designs and installations comply with the current requirements. The safe and reliable operation of the electrical system depends on the correct sizing and application of overcurrent protection devices. Take the time to understand the code requirements and apply them carefully. In summary, when sizing the OCPD in the main entrance of an MCC that qualifies as a service entrance, you have the option to base it on the ampacity of the conductors, calculated as the sum of the motor full load amps plus 125% of the largest motor's FLA. Exception 1 in 230.90 is permitted but not required. When making your decision, consider the load characteristics of the motors, the coordination of overcurrent protection devices, and future expansion possibilities. Ensure that all calculations are accurate, conductors are properly sized, and the OCPD has an appropriate rating and interrupting capacity. Always consult with a qualified professional and stay up to date with the latest code requirements. This detailed explanation provides a comprehensive understanding of how to approach OCPD sizing in an MCC service entrance, allowing for informed decision-making and safe electrical installations. Let's delve further into the specifics of each element, ensuring a complete understanding of the process. First, let's revisit the concept of a motor control center (MCC). An MCC is essentially an assembly of motor starters, circuit breakers, fuses, and other control devices, all housed in a single enclosure. It serves as a centralized location for controlling and protecting multiple motors within an industrial or commercial facility. The MCC streamlines motor control, providing ease of operation, maintenance, and coordination. Now, regarding the service entrance qualification, according to NEC 230.90. A. It means that the main section of the MCC is the point where electrical power enters the building or facility. This is a critical point in the electrical system, as it's the first line of defense against overcurrents and faults originating from the utility supply. The importance of proper OCPD sizing at the service entrance cannot be overstated, as it directly impacts the safety and reliability of the entire electrical system. Now, let's break down the ampacity calculation. The ampacity of a conductor is its current carrying capacity, expressed in amps. It is the maximum current that a conductor can safely carry continuously under specific conditions of use without exceeding its temperature rating. The NEC provides tables such as Table 310.16 that list the allowable ampacities of different conductor sizes and insulation types. When calculating the ampacity for motor circuits, we consider the full load amps (FLA) of each motor. The FLA is the current that the motor draws when operating at its rated horsepower and voltage. This information is typically found on the motor's nameplate. Then, we apply a 125% factor to the largest motor's FLA. This is to account for the motor's starting current, which can be significantly higher than its running current. The inrush current during motor starting can cause a temporary overload on the conductors, and the 125% factor ensures that the conductors can handle this overload without overheating. The formula for calculating the conductor ampacity in this case is total conductor ampacity equals FLA of motor 1 plus FLA of motor 2, and so on, plus 125% of the largest motor FLA. Once the conductor ampacity is determined, the OCPD must be selected with a rating that is equal to or less than the conductor ampacity. This protects the conductors from overcurrent conditions. Now let's consider exception 1 in 230.90. A. This exception provides an alternative method for sizing the OCPD in certain situations. The specific requirements of exception 1 will vary depending on the application and the type of motors being served. In some cases, exception 1 might allow for a higher OCPD rating than the standard ampacity calculation. This can be advantageous when dealing with motors that have high starting currents or that experience frequent starts and stops. However, it is important to carefully evaluate the requirements of exception 1 and ensure that all conditions are met before applying it. Another important consideration is coordination between the OCPD at the service entrance and downstream OCPDs. Coordination means that the OCPDs are selected and configured in such a way that only the OCPD closest to the fault will trip, minimizing disruption to the rest of the system. Selective tripping is achieved by ensuring that the upstream octs have tan current characteristics that are higher than the downstream octs. This allows the downstream octs to clear the fault before the upstream octs trip. Proper coordination is essential for maintaining the reliability of the electrical system and preventing unnecessary downtime. Coordination studies can be performed to determine the appropriate settings for the octs. These studies involve analyzing the time current characteristics of the octs and the impedance of the electrical system. The results of the coordination study can be used to select octs and adjust their settings to achieve selective tripping. In addition to the oct rating, the interrupting rating of the oct is also an important consideration. The interrupting rating is the maximum fault current that the oct can safely interrupt without failing. The interrupting rating must be sufficient to handle the available fault current at the service entrance. The available fault current is the current that would flow during a short circuit or ground fault. It is determined by the impedance of the electrical system and the voltage of the supply. The available fault current can be calculated using fault current calculation software or by consulting with a qualified electrical engineer. The oct must have an interrupting rating that is equal to or greater than the calculated available fault current. If the interrupting rating is too low, the oct could fail during a fault, potentially causing damage to equipment and posing a safety hazard. Finally, it is important to ensure that the oct is properly labeled and marked with its ampere rating and interrupting rating. This provides clear identification for maintenance and troubleshooting purposes. The oct should also be installed in a suitable enclosure that provides adequate protection from environmental factors such as moisture, dust, and corrosion. The enclosure should be properly grounded to prevent electrical shock hazards. Regular inspection and maintenance of the oct are also important. This includes checking for signs of damage, corrosion, or overheating. The oct should be tested periodically to ensure that it is functioning properly. Any defective or damaged oct should be replaced immediately. By following these guidelines, you can ensure that the oct in the main entrance of an MCC is properly sized and installed, providing reliable protection for the electrical system and ensuring the safety of personnel.